Hello and welcome to video 3.3, Dissipative Forces and Conservation of Energy. Now we've talked about conservation of energy previously, but now we're going to look at it with a little bit more detail in terms of what do we do when we have these things called dissipative forces, and what are dissipative forces for that matter. Well, recall that work is done when energy is transferred from one object to another. Also, that the law of conservation of energy states that the total amount of energy in a system does not increase or decrease in any process. And finally, we've also been talking about this work energy theorem that says that work done on an object is equal to the increase in energy of the object during a process. So all three of these things are interconnected and are related to each other, and they are now accepted ideas in physics. However, it was not all that long ago when this was not the case, because all of these things require that mechanical energy not change in a system, or so they thought. But what about when there are forces that do decrease the mechanical energy in a system? Not the total energy, but just the mechanical energy. Remember at the very beginning of this unit, we talked about all the different types of energy, and I said we're going to ignore most of them for the moment. Well, now we have to come back and think about them a bit. So what if we had something like friction or thermal energy? Friction or thermal energy, as I said before, decrease the mechanical energy in a process. It wasn't until there was an understanding that friction and thermal energy are actually types of energy that can relate. Well, friction is a force that causes a type of energy, thermal energy, heat, that is in fact, if we take it into account, allowing the law of conservation of energy to exist. So once friction and thermal energy were understood, conservation of energy was accepted, and at this point in time, conservation of energy holds true for all known processes, which is really cool when you think about it, because so many of the other laws and rules in physics only hold true within a certain boundary. But law of conservation of energy seems to be one that holds true everywhere. Friction and thermal energy and other types of things that cause a decrease in mechanical energy are what we call dissipative forces. Dissipative meaning that they get rid of. So they decrease our mechanical energy, meaning that they're getting rid of some of our mechanical energy. It's not going away completely. It's not disappearing, but it's changing to a form that we don't typically think about. So let's take a look at how this appears in an equation. If we have, for example, if we start with the work energy equation, we can say, and I'm going to say work NC, meaning non-conservative, because originally friction was considered a non-conservative force, so the work would then be non-conservative. So if we have non-conservative work, then it should be equal to the change in kinetic energy plus the change in potential energy. Keep in mind that we now know that non-conservative work is due to friction, and therefore it is equal to the negative force of friction times distance, and it's negative because it's going to be in the opposite direction of motion. So then that is going to be, again, equal to our change in kinetic energy, which would be 1/2 mv2, or final squared, minus 1/2 mv0 squared, because that would be our change in kinetic energy, plus mg final minus mg y0. This takes into account all of our different energies. We have all of our different works. We have the work due to friction is equal to the changes in the kinetic and potential energies. If we rearrange this to put initials on one side and finals on the other side, we end up with 1/2 mv0 squared plus mg y0 is equal to 1/2 mv final squared plus mgy final plus force of friction times distance. This equation showing that our initial works or energy is equal to our total of finals is both the work energy theorem and the law of conservation of energy. It's basically showing that they are the same thing. So why do we have two of them? Well, that's because depending on the situation we're looking at and how we are interpreting the situation is going to determine whether we want to think of it in terms of the law of conservation of energy or we want to think of it in terms of the work done turning into energy in the system. So you'll see both of these being used, and mathematically they're the same thing, and conceptually they mean the same thing. It's just your perspective that's going to make the difference between them. Okay, let's take a look at an example here about a roller coaster. We have a roller coaster that starts up here at position 1, a height of 40 meters above the lowest point of the roller coaster track. However, when it gets up to the other side, it momentarily stops here at a height of 25 meters. And then the engine kicks in and it starts to move. You know, the gripper hook gets it and it starts to move again. But if we stop it right there, if we take a look at position 2, where it stops for just a minute, we can figure out the total, or we can estimate the total frictional force on the car. We have to first know that the distance from point 1 to point 2 is 400 meters. We also have to know that the mass of the car is approximately 1,000 kilograms. And again, we are going to be trying to find out what is the total force of friction on the car that would cause it not to be able to get up to the top of the hill by itself. And we know that in real life that this is absolutely what happens, because if you've ever been on a roller coaster, you get 3/4 of the way up or maybe a little bit farther, and then something has to happen to continue it moving. All right, so to start with, we are going to have to keep in mind the initial speed up here is 0. We are also going to have to keep in mind that 40 is the initial height, and the final speed here is also 0, and the final height is 25 meters. And then, as I said, 400 meters is the distance. If we use the equation that we ended with on the last slide, we can then say that 1/2 mv naught squared plus mgy naught is going to be equal to 1/2 mv squared plus mgy plus FFD. If we go ahead and plug in our numbers, we get 1,000 times 1/2 times 0 plus 1,000 times 9.8 times 40. Well, that whole first term goes to 0. In fact, this first term on the other side is also going to go to 0. So what we really have is 1,000 times 9.8 times 40. Sorry, that should be 0. Minus 1,000 times 9.8 times 25, all divided by D of 400, and that is equal to our force of friction. If we plug in all of those numbers and we round a bit, then because it's an estimate, we can certainly do the rounding. The force of friction on the roller coaster is approximately 370 newtons. So in this situation, we start with a situation that you have initial and final speeds being 0, which means that you're going to have to wonder, well, what the heck am I going to do with it? And again, if we were to look at this with kinematics, it would take us quite a long time to figure this whole thing out. But keeping in mind that dissipative forces are a thing, i.e. friction is a thing that we have to keep in mind, and that energy conservation and the work energy theorem are basically the same thing, we can end up solving some pretty complicated problems here. With this, we could actually go further if we wanted to. We could find out what the coefficient of friction is on the track. We could find out the normal force on the track at 0.2. We could find out all sorts of other stuff. But for the moment, we're not going to. This is all that you're going to need to know how to do that relates conservation of energy with dissipative forces. So bye for now.